Good morning or good afternoon, depending on where you are at. My name is Atarot Azizi Namini, Director of the ABC UTC at Florida International University. Today we have a little more detailed information about our 2021 virtual ABC conference. It's just only a couple of weeks away from now, so if you have not registered, please go ahead and register ASAP. That will really, truly will help us. The conference, the focus is on the international case studies, information, research data, and so on. So it really provides you with an opportunity to see what the rest of the world is doing in the ABC area. Please note, we will not archive the presentation. So this is your only chance, basically, to see what the rest of the world is doing in the ABC area. The staff have worked diligently, and we have put together an excellent program that hopefully you will register and you will attend. We are going to give you some example of the keynote talks that's going to be given. There are 16 keynote talks. Eugene Burweiler with Swiss Federal Institute of Technology is going to discuss the UHPC for bridge deck overlays. The whole concept was developed in Switzerland, and he's going to discuss both projects, case studies, and also what is next and the research and development in the area of the UHPC for bridge deck overlays. We are going to have an excellent presentation summarizing everything in China that is doing in the ABC area. So Liang Zhong, he was a chief engineer at the Shanghai Urban Construction Design and Research Institute, is going to give us a very comprehensive presentation on the ABC in China. Peter Collins in Sweden is going to give us some really innovative concept for prefabricated elements and the modules for ABC. Mike Schelling of the Technical University of Berlin, and I visited his lab, and they are doing some wonderful work in the area of the ABC, specifically the small segments that is actually built and then post-tension together. So he's going to give us a very good summary of the work in Germany. Other presentation that's going to include in the conference, Miguel Ortega will be given an ABC for high-speed rails. So it's a very good opportunity to your contractors and so on that may get involved, especially on the West Coast, to see this. Talking about the West Coast, Dory Mellon and Jay Holombo will be presenting the new Caltran ABC construction manual that has been rolled out. There are many interesting work is going on in the development of new equipment for ABC in China. So Hu Shudong will be giving a presentation providing a summary of new equipment that are being developed for ABC use. And then we have Laurent Bjorn that's going to give us the case studies and the UHPC field application in Switzerland, both for retrofit, the overlay, and so on. The conference is going to include a workshop, very interesting workshop that's going to be hybrid. It's going to have it physically. You're going to see how it feels to make a UHPC when you mix it and so on. The ABC UTC researchers, we have developed a non-proprietary version of the UHPC. In addition to us, many others have also developed a non-proprietary UHPC. This workshop is going to allow you to see what we at the ABC UTC have done. Also, 6 other universities that have developed independently non-proprietary UHPC. This includes University of Connecticut, University of Arkansas, University of Michigan, Arizona State University, University of Nebraska-Lincoln, New Mexico State University. So you will see that how simple it is to make a UHPC and how simple it is to have your ready-mix company in your area to make a UHPC. Our objective is to show that this is hopefully within the next few years, it's going to be almost just like you're making a regular concrete. So please encourage your ready-mix companies in your area to attend and register and attend the conference. So in a glance, 16 keynote talks, 30 presentation. It's going to be very entertaining. There's going to be music of the world in between the presentations. We are going to have a spotlight on the exhibitors. So if you would like to exhibit, please contact our staff. Like I said, the UHPC workshop, award programs, and the reception, and of course, the exhibit hall. We also would like to, we are very happy to tell you that in 2022, finally, we are going to be getting together face to face. So the call for abstract for 2022 is up. Go to our website. Please consider submitting an abstract. Again, in summary, please assist us by registering early. If you have enjoyed all these webinars that we have held over the last 10 years, please show your support, register and attend the conference. And please note that each registration is for one attendees only.
Our presentation today features Arkansas's ABC and first lateral bridge slides replacement project. We're pleased to welcome our presenters, Rick Ellis, State Bridge Engineer with the Arkansas Department of Transportation, and Fred Harper, Department Manager for Bridges with Michael Baker International. Rick?
Good afternoon. Again, my name is Rick Ellis, the State Bridge Engineer for the Arkansas Department of Transportation. My co-presenter today is Fred Harper, Department Manager for Bridge at Michael Baker International. Thank you for joining us today. I'll provide a brief discussion of the first 6 projects on this list. Fred will discuss the last project, our feature presentation. Some of you might ask, where is Arkansas? Arkansas's eastern border is the Mississippi River. Our neighbors to the north and to the south are Missouri and Louisiana, respectively. And to the west, we have Oklahoma. This is a list of the committees, conferences, showcases that Arkansas Department of Transportation has been involved with. Many of these may be familiar to some of you. I highlighted in green our RDOT FHWA ABC committee. This is a team that was assembled by our local FHWA bridge engineer, Terry Daniel, and our state bridge engineer, Carl Fuselier, both now retired. The team included representatives from FHWA, RDOT, design consultants, fabricators, and local public agencies. During this committee, we developed our ABC evaluation criteria and flowchart, and a list of ABC methods that we would like to consider for use in Arkansas. RDOT's ABC policy was implemented by our Deputy Director and Chief Engineer on April 24th, 2014. Our first project that I would like to highlight is the Broadway Bridge replacement that was let in September 2014. It was designed by Garver Engineers and HNTB. It was twin basket-handled tied arches. And the project location is downtown Little Rock over the Arkansas River. In our presentation today, you'll hear a lot about our site use A plus B plus C special provision. I'll discuss that a little bit in depth here so you'll know what those letters stand for going through the presentation. A is the contract dollar amount. The B for RDOT is a subset or unique item within the contract that needs to be expedited. And C is the total contract days. For this Broadway Bridge job, the contractor was allowed to close Broadway Street, a major corridor over the Arkansas River between Little Rock and North Little Rock, for 180 days at $80,000 per day. The contractor received incentive as he only closed the route for 154 days. We're quite proud of this bridge. This slideshow just shows a small sampling of the attention it received. Our first use of prefabricated bridge elements is at the King Bayou. This is a bridge in southeast Arkansas. Our options were to construct a seismic temporary bridge or close the highway and use ABC. We had a reasonable detour, so we chose to close the highway and use ABC. We used precast bent caps and precast abutments, precast concrete channel beam superstructure units. The photo on the bottom right of the page shows the precast units. Photo on the top left of this slide shows the precast abutments as well. We used pile pockets that were set down on concrete filled steel shell pipe piles. And the finished structure is shown in the bottom right. The highway was closed for 148 days, and this was extended due to flooding and backwater from the Arkansas River. Our next ABC project was also prefabricated bridge elements, but this time we used it for repairs. 6 of 17 of the spans of the bridge shown on the slide were heavily damaged by fire. We let this job in May of 2020, and the designer of record was Garver Engineers. This just shows a cross-section of the existing bridge superstructure. Our maintenance of traffic options were a detour, which was too long, constructing a temporary structure, which for a 425-foot long bridge was too costly, or to use ABC. And we chose to use ABC, and we had to maintain one lane of traffic at all times with traffic lights at each end of the bridge. And we completely replaced 6 spans that were heavily damaged by the fire. This is what we found on site after we were able to give the bridge a good cleaning. The bridge was load posted to keep heavier trucks off until repairs could be made. The foundation element is steel HP piling encased in concrete, and the piles were not damaged by the fire. This slide shows multiple pictures of the precast bent caps that were used. Because we had to do this in stages, notice the couplers on the top right photo. For this job, we also chose to use steel modular units. The plan was for 2-beam modular units that you typically see. Because of the short spans only being 25 feet and the lift being pretty light, the contractor proposed to use 4-beam units, and this was approved by the state. This slide shows the almost finished structure. The last step is to paint the ends of the weathering steel beams. We also used the A+B+C SB in this project, and the incentive disincentive was $500 per day, and we allowed the contractor 75 days to complete this work. Challenges led to an extension to 131 days, and the contractor only used 122 of those. The challenges dealt with the surface of the 2 existing caps that remained. They were intentionally roughened in the initial contract, and so in order to place the new modular units on the bent cap, there had to be quite a bit of modification. Some more prefabricated bridge elements, this time on Isabel Creek. The precast abutments were fabricated before the bridge closure, and it consisted of pile pockets over top of H piles. The planned closure was 100 days. We intended to construct the drilled shaft intermediate bends and the columns prior to closing the route to traffic. And when they were constructing the drilled shafts, one of the 6 actually interfered with a spread footing. So we had to extend 55 days to closure. The incentive disincentive was $2,000 per day. Here's a photograph of the drilled shafts and columns. Again, they were constructed outside the footprint, and the existing bridge was very narrow. Precast bent caps were also fabricated before bridge closure, and the column reinforcing extended into pile pockets. And superstructure construction was conventional. This is another ABC project. It's under construction currently. We're using partial depth deck panels on pre-stressed beams. It's not really specifically for ABC purposes, but we like the idea of the panels and wanted to try them out on a project. We have 2 more jobs being let in 2022 with partial depth deck panels. This is our 2018 Competitive Highway Bridge Program grant job in Mississippi County. Arkansas was one of 25 eligible states for the grant. The selection criteria was bundling, innovative technologies, structural condition, and support for economic vitality. For bundling, we had 9 bridges and 5 box culverts proposed for the job. For innovative technologies, we proposed to use accelerated bridge construction, and this consisted of precast bent caps, a very high seismic region, prefabricated modular steel bridge units with ultra high performance concrete closure pores and connections. For structural condition, all 14 of the structures were either posted or pour and posted. For the economic vitality, Mississippi County is a heavily agricultural area, as can be seen on the next slide. This project is currently advertised, and plans and specifications can be seen on our website. For maintenance of traffic, we will have multiple stages. We intend to close 2 sites at a time. The green pins represent bridges in the job. The red pins represent box culverts. There's approximately 13 miles distance north and south between the most extreme sites. For bridge closure sites, we're allowing 120 calendar days, and for box culvert sites, we're allowing 20 calendar days. Challenges on this project were 3 different bridge widths, 4 different span lengths. We had both square and 3 different skewed bridges. We have 3 different pile diameters. The incentives and disincentives range from $2,500 per day to $17,000 per day, depending on road user cost at a particular site. My last slide is just a snapshot from the plans of a typical bent and a typical roadway section. We seriously considered using next beams for this project, but the combinations of span lengths, roadway widths, and skews seem to direct us to modular units. That is the last of my slides, and I will be turning the presentation over to Fred Harper. Thank you.
Good afternoon, everybody. My name is Fred Harper, and I lead the bridge design group for Michael Baker International out of Little Rock, Arkansas, and it's a pleasure for me to be here with you today to share this exciting project. So the feature project today is the Interstate 30 DeRose Creek Lateral Bridge Slides, and we're very pleased to be called upon by RDOT to help them out with this project. Our company has some history with doing a lot of ABC work out in Utah. I know they're very progressive out there, and have tried out a lot of new things, and we're able to lean on their experience for this project. So I wanted to give some background on the project location. This DeRose Creek project is located on Interstate 30, just to the southwest of the capital city of Little Rock and the small town of Arkadelphia. This also, as you'll note, is on a major truck corridor between Little Rock and Dallas. Carries about 30,000 vehicles per day with greater than 50% trucks. So this site served as a great location for the department to try out this ABC work. There was enough demand there to justify the use and added expense for this construction method. So I wanted to give some background on the planning part of this. So RDOT had, before it even came to us, had decided that this would be an ABC project, and Rick had given some good thought to how that might actually be constructed. And as part of our work when we first got on this job, we were assigned to do a bridge construction staging study. So we were going to decide not only that we would do ABC, but to think more about the details and how that would be done. So Rick had the initial idea to construct one of the bridges using ABC, and then to build the other bridge conventionally. So we took that option, that's our option one that you see on this screen here, and that ABC bridge would be staged in the median. So that was our option one, and we had an option two here that was similar, except that it staged that ABC bridge to the outside of those twin bridges. And then we also wanted to consider sliding both bridges and staging them both to the outside. So that's what's represented by option three. So we've got some color coding here that hopefully will make the time benefit stand out. So we've got the green indicating just the construction time for the various phases of work. We've got the orange color that represents not the head-to-head closure, but a time period where we might have traffic in some type of disruptive pattern, whether it be a crossover from one side of the interstate to the other. So you can see from this slide there's a massive time benefit for option three. So we've been able to do all of the staging work, substructure work, without even touching the interstate traffic. So we get down to a very small head-to-head closure, which is represented by the red dots, which are a little bit hard to see here because it's such a short time right here on this bottom. So you can see the massive time benefit that ABC would provide on this project. So the last slide was the idea that we had at the planning stage, and went ahead and put together the actual construction timeline. And as you saw from the last slide, we had the eastbound and the westbound bridges working in sequence, and in reality it ended up being a lot more overlapped with the schedule. So we had the substructure that would be constructed that would suit for both bridges, and then the new superstructures were built nearly concurrently. So you can see overall we ended up with a total construction timeline of about just under a year. So it was quite a bit more abbreviated than what we had initially assumed. I want to show a little bit about the bridge layout here to give you some of the details. We've got existing bridges that are 3 spans, 3 70-foot simple spans. Was the existing span arrangement. So as part of the project, and similar to any other bridge project, we did a type and size study to figure out the best option for replacement. We looked at a 3-span option, which would have to have, of course, a different span arrangement. And we also considered a single span alternate. So we ended up going with the single span option for several different reasons. The first of which is that it simplified our slide process, not having to coordinate moving multiple spans, which for a 3-span like this, we would typically design a continuous superstructure there. So not having to coordinate jacking between multiple bents and really watch that and have very tight tolerances. We're fortunate in this case that the geometry and our vertical freeboard to the design floods were ample enough that we could afford to drop that low chord down a little bit and utilize a simple span. You also see with the highlighted yellow that we've got horizontal curvature on the project. It's a 1/2 degree horizontal curve, and we wanted to maintain that in our finished deck so that we would have a smooth roadway geometry, while at the same time we wanted to keep our structural framing and the slide process as simple as possible. So we elected to actually cord these steel plate girders, and as a result of that, of course, you're going to have some varying cantilever dimensions. You can see with the red dots on the screen right here that we have elected to use a straddle bent substructure. So those are going to be constructed in the existing end span. So we're actually shortening this bridge, and that was carefully checked, of course, with the hydraulics. And we had actually fairly comfortable headroom with working in those end spans. So it worked out very good. After those drilled shafts are in place, we're going to come in and you can see the location of our straddle bent caps. So one little aside I wanted to talk about is that this project actually went through a couple of different iterations here. The first time that it was designed, the concept was to come back with our typical 40-foot clear roadway width to essentially replace in kind what was there. And then about the time that we got to our 90% plan review, the department came back and the planning folks had elected to go ahead and widen these things for 3 lanes, a future 3-lane widening. So that was I feel like really wise decision there to go ahead and take care of that at that point. With the detailing and the design being so critical, this would be a very challenging bridge to widen at a later point. So there were a handful of things when we were doing the design of this project that we wanted to keep in mind, and the purpose there is to, at each point and at each component of the design, to see if there's a way for us to trim out any time, and specifically with the short-term closure period. The initial concept when we were going into the bid letting was that we were anticipating about a 3-day closure, a long weekend, about 60 hours. So with a fairly congested time frame, we had to shave as much time out of that as possible, to do as much work before the closure as possible. So I wanted to go over a couple of these things. Lengthened approach slabs. So the existing 3-span bridge had approach slabs, and with our shortened bridge, we elected to lengthen the proposed approach slabs such that they would give us a lot of benefit with our roadway work. So those new approach slabs actually extended beyond the limits of the existing, such that the roadway approach work would only consist in milling and in overlay, asphalt overlay operations. So that would really speed up the process there. We specified higher strength concrete in the approach slabs, specifically for the portion that was going to have to be opened within the 3-day period. We also used a precast approach gutter on the side that would be opened first and would have to have a quick connection to the guardrail. As you'll see later, that did not end up being used, but that was the initial concept to meet the 3-day schedule. Looking in the lower right, you can see the special end bent backfill that we used, as opposed to an SM1 or a Class 7 type material, which is commonly used. We ended up using something more akin to a railroad ballast. So it doesn't have the percentage of fines in there, and it can be compacted much more quickly, and it's also free draining, which is good. At this point, I'd like to go through the lateral slide construction sequence and show you step by step how this thing came together. So starting off on this first slide, I'll kind of introduce the scheme here. So in the upper left of these slides, we've got a 3-dimensional microstation drawing that we produced as part of the design process, and these all have the components separated out where we can see step by step how this thing was to be constructed, and it's pretty remarkable how similar it turned out. And then, of course, on the lower right, you can see the as built construction condition and see what that looked like. So the first step in this project is to drive permanent steel casing for the drilled shafts. We've got a moderate amount of overburden, and then we are fanning this bridge into a sandstone and shale bedrock, so the permanent steel casings were driven down and seated into that rock initially. After those are in place, it's time to do typical drill shaft construction, auger bits to remove the overburden material, and then rock coring bits used to create the rock socket. So you can see in the lower right hand corner, we've got the drilled shaft reinforcing cages protruding on the bottom there. It's actually a mud slab. That's not part of the design cap. That's just a mud slab to give them a nice clean working area under that bridge. And you can see we actually ended up with fairly comfortable working headroom, even though it is obviously going to be more labor intensive to stick build a cap underneath an indent like that than being able to lift it whole in place. After the drill shafts are in place, it's time to build the straddle bent end caps or bent caps. You can see that we've still got a good amount of headroom there for them to work. Wing wall piling was required on this one. The fact that we're shortening the bridge from the original 2-den down to 170-foot simple span, it's going to necessitate a lot longer wing. We ended up with a 25-foot long wing wall, so we had to have the wing wall piling to support that weight. Next come the in-bent wing walls. And you can see here, let me get my laser pointer, that part of the idea with these is to build as much of this the wing walls and then these little front facing walls, get them as absolutely as close to the existing bridge as we can. We also had to construct a center wall in the median that would eventually line up with the semi-integral back walls. At that point, it's time to start working on our temporary false work. So we had originally we had a conceptual drawing and construction phasing in our plans that really just spelled that out schematically. With this being a design bid build type contract, we didn't dictate real specifically exactly what the false work design would be and exactly what the lift and the slide system would be. We wanted to give as much flexibility as we could to the contractor with their preferred means and methods. This was pretty close to our assumption what they ended up doing. You can see in the lower right, they've driven a double row of H piling for their temporary caps. It ended up being fairly conventional cap, but again, with a design build approach, you could probably have a lot more upfront communication and potentially, be able to pass some more ideas about different ways to do that. But it ended up being fairly conventional cap that was used for the temporary. Okay, so after the piles are in place, they're going to construct the temporary in-bent caps. A couple things to point out: the importance of the geometric control is crucial. We've got to have our geometry dead on with our in-bents, parallel direction, level, and smooth surface that was within a fairly tight tolerances as memory serves. So it's very important to get all those things right before we think about shutting down traffic. So after we've got the temporary false work in place, it's time to start building our proposed superstructure. And as I mentioned earlier, this is a semi-integral in-bent configuration. So we've got a couple different pores that we handle that in. The first pore, the lower part of that diaphragm, as you can see in the lower right picture, we've got some steel shoe bearings that are just temporary. They will eventually be encapsulated in that concrete end diaphragm. You can also see the steel plate girders in the background there. After that first pore is in place, it's time to install the steel plate girders. We use a 69-inch web depth weathering steel, grade 50 girders for this project, and you can see the relative scale with the iron workers there in the upper right picture. Another thing I wanted to point out while we're on this slide is the 8-inch diameter corrugated duct that we have running through our end bent diaphragm. So the purpose of that has to do with the lateral slide move system. So the contractor and their subcontractor elected to use a pre-stressed strand with jacking frames and strand jacks to actually move this bridge laterally. So that duct right there is for where those strands would pass completely through that diaphragm. Once the girder is in place, we're going to do the second half of the semi-integral end bents. So you can see we took that to the top of the slab and did about a 5-foot section of the slab. Next, we're going to pour the balance of the bridge deck. You can see this is fairly typical construction with pump truck and bed well screed that are completing that work. After the bridge deck's in place, we're going to install the single slope railing. So this is 3.5 foot tall interstate railing right there that we've got on that bridge. Again, just want to emphasize the point that we're trying to complete as much of this work as we absolutely can before we close the traffic. We want to maximize this part and minimize the work that we're doing in the short-term closure period. So as we're getting closer to being able to do a slide, one of the things that they're going to have to do, because of course we have to slide these things one at a time, and as part of that, we had originally envisioned the contractor using a steel sheet piling in the median that would encapsulate the backfill for the first phase of the work, and then when the second bridge would come in, they could remove that. So an interesting little wrinkle and difference from our initial thought is, if you look in the bottom right picture, you can see instead of using that steel sheet piling, that the contractor elected to essentially build themselves a little gravity wall with some used portable concrete barriers. They just battered that thing back, it stepped it back, and it seemed to work really well. So I'm always amazed at the innovations that the contractors can come up with. After the sheet piling's in place, we're ready to start the short-term closure. And of course, I want to take this opportunity just to emphasize the importance of the pre-planning. We had on this job, we had special communication plans, we had contingency plans, and there were several parts of that. It was much heavier on the front end with the pre-planning, and just want to emphasize that and keep that in mind, because once the traffic is moved over and we start demolishing the bridge, there's no going back, and you can't not deliver. So we have to make sure that we can get there. So you can see here that once that side of the interstate was closed, we're going to have head-to-head traffic on the opposite bridge that is still in service. We initially envisioned this as a 3-day window, but as it turns out, through the initial bidding process and through the letting and communication with contractors, that was relaxed a little bit. So the winning contractor ended up bidding, if memory serves, 10 days, and they ended up completing it in 8. So there was a little difference there, but still very, very pleased with a fast product there. After that bridge is demolished, we can slide it over, and this actual slide process took about 10 hours. Started early in the morning and very late afternoon they were done. So yeah, it's kind of slow and fast at the same time. I mean, it's one of those things you don't want to go lightning fast and damage your structure. So they were able to do that, and things went very smoothly. So you can see in the lower right picture, this westbound bridge is about halfway home. You can see it. We got that outside wing wall about midway through the bridge deck there. I'm going to take a minute to talk about the actual lateral slide mechanism that the contractor ended up using. So since we had the design bid build project, we used a special provision to to set up the process for designing the temporary works in the lift system, in the lateral slide system. And the contractor chose to partner with VSL Structural Technologies, and they did the final design for the reaction frames that you see in the upper left picture, and then also the lift system to lift the bridge in the lower right. As part of giving flexibility in the plans, you can see the jacking pockets that we had detailed in the lower right picture. So those pockets are placed between the girder lines, and there's enough room in there for them to get the jacks in there. And also there was an option in the plans for a Hillman roller. So in the plans we envisioned them using either the PTFE and stainless steel slide surface or a Hillman type roller. So those pockets were detailed in there to give them flexibility, again, not knowing exactly what their preference would be. One thing I wanted to point out here that was really neat, there was a lot of controls with this coordination, as you can imagine. You know, when we've got multiple points of jacking that have to be coordinated very carefully, they had the control center up on top of the bridge, which I'll show you in a minute. All the hydraulic lines, they had a manifold to make sure that the pressures were even to all these things. So of course they're monitoring pressure up on their controls. And then you can see right here, they actually have a little distance measurement too, so they can also make sure that we're having even jacking between all the bearing points. In the left picture here, you can see the hydraulic controls. That's one of the VSL workers that is running the lateral slide operations right there. So he's got gauges to monitor what's going on. And then in addition to that, we've got the old-fashioned, tape measure method to check that. So we had several ways to make sure that this thing was going according to plan. The right-hand picture, you can get a good view of the entire system. At the very bottom, we've got one of the reaction frames that VSL designed. And we've got this bundle of stressing strands right here that went from outside to outside of the temporary false works. Altogether, this whole system was nearly 300 feet long, and of course, it takes a tremendous amount of force to move this thing. And then one thing you might notice in this picture, this is taking during one of the move cycles, and you actually see that it's a little bit slack in there, which is another thing that again we know by theory and calculation that it's going to do that, but it's always really interesting to see it in real life, to see those cables get loaded and sometimes would be completely slack on the ground on the back side of that tension there. Okay, so after the westbound bridge is moved into place, it's time just a few weeks later to switch over. Traffic was moved over to the new bridge, 2 lanes of traffic over there, and it's time to deal with the eastbound bridge. So it's going to be demolished in a similar way. After the old bridge is out, it's time to move over the new bridge. And these are some of the final details that I was really excited to see. Had a magical special chemical there in the lower left that really helped this process along with the Dawn dish detergent. That was one thing that was always really interesting to me, and it was quite comical to show up the day of the slide and see that the guys had bought out the local Dollar General with about 20 yellow bags of Dawn dish detergent. So that was a key component to our success that day. So you can see the Dawn dish detergent there in the lower right picture. We're getting very close, within just a few feet of our target location. And then in the upper right is when we were literally within an inch. As it turns out, on this eastbound bridge, I watched them take this picture. I watched it go to its final location, got within about a 1/4 inch. So we were really happy with that. So you can see with the jacking strands on the strand jacks on the lower left, with the blue painted jacks there. We actually had those on both sides of our semi-integral end vents, and the purpose of that was a requirement in the plans to be able to reverse direction if we need to, if they happen to overshoot their final location. Fortunately, those were not needed, but I do think that was a good decision to have those just in case they might have been. And here's a picture of our completed construction. As you can see, this is taken about a month after they finished up and got the grass all seeded, and looks really nice and clean. And to the traveling public, it's going to look very similar to many other new highway bridges. But as a structural engineer, you can get down there and see the differences and appreciate all the extra work that went into an ABC construction. I want to go over a couple slides here with the key players. RDOT being the owner, Michael Baker, us as the designer. Prime contractor was Manhattan. WW AFCO Steel out of Little Rock was a steel fabricator. And then, as I mentioned earlier, VSL was a specialist for the bridge lift and the move, the lateral move. So with any project, you're going to have some challenges and lessons learned. Overall, we're happy that this project went very smoothly. There weren't any major issues or delays. Like with any project, I mean, there's going to be some some imperfections with construction that they're going to have to overcome. One thing that I wanted to stress here is not so much of a lesson, but just I guess it kind of is a lesson learned. It's one thing that we appreciated that went well is just the critical planning with the geometry, particularly with this one being on a half-degree curve. We had a specific staking layout, staking diagram for them to make sure that we got everything positioned correctly. And it did, but it was one of those things that took a lot of concentration and to make sure that we had everything where it needed to be. As part of our special provisions for the slide plane, we did a test slide, which I think is a great idea. So several days before the first slide, we actual slide enclosure, we did a test slide, or we just moved the bridge about 3 inches laterally and then brought it back just to make sure that all the equipment was working correctly. We had a contingency plan during the lateral slide that VSL produced and the state and we reviewed to make sure that it conformed to the design plans, and it had additional equipment that they might need if something were to break down. Again, there's no going back. They've got to be able to deliver. And we had a lot of increased communication between the key players. We had several meetings as part of the construction process before the actual slide to make sure that everyone was on the same page. Of course, the communication is key. We had everybody on speed dial in case anything was needed during that time period. So I had a quick time lapse that I wanted to show to the group here of the actual slide process. You can see we started early in the morning with the slide. And as the bridge is moving over, if you look in the lower right-hand corner behind the John Deere track hoe, you can start to see the white Teflon track that's being picked up as it's moving along there. You can see at that point we're about there right there. Okay, and at that point that concludes our presentations, and we're open to questions.
All right, thank you, Fred and Rick. Excellent presentation. At this point, we're gonna have Paul Lyles and Jugish Kapoor to moderate the question and answer period. Paul?
Okay, thank you, Ettore, and real good, Rick and Fred. It's really a neat project. We have some questions that came in pre-webinar, and I'll go in and ask those, and I think then Jugash is going to handle them after that. The first question we have is how much contractor engagement occurred before the letting, and how prescriptive were the plan drawings for the temporary structures and move sequencing?
I think I can handle the excuse me, the first portion of that about the contractor engagement. I don't think there was very much specific contractor engagement for this specific lateral slide job. On slide 3 that I showed, one of the items was a workshop for ABC in 2016. After that workshop, I was able to give a presentation to our contracting community and provide a slideshow where I showed them different methods that we were considering using on bridge construction jobs in Arkansas. And so that gave them a little bit of preview of what was coming up. And we also used a extended advertisement period before this project. And we have a mechanism to allow contractors to ask pre-bid questions during that time. And then we provide a response and make that response public. Now let Fred handle the rest of the question.
So yeah, I was just going to add to that. We did have a couple of pre-construction presentations that we gave on the project when it was still in design, and it was, of course, didn't have any construction to show at that point, but we did have a chance to showcase that, and I know at least some of the contractors did see that, so I think that did help give some exposure. Okay, and then for how prescriptive were the plan drawings? So again, the idea with this being a design bid build is to keep them as flexible as possible. So we showed the schematic concept and had in our special provisions for the lateral slide the objectives and constraints we wanted them to achieve, but then that required the contractor to submit their slide plan, which was reviewed, and that got into the nuts and bolts of exactly what they would use.
Okay. Second question was, please address if and to what extent the design stage and plan preparation activities were subjected to peer review.
So yeah, like any other project, we subjected the design and the plans to multiple reviews within our company. So we had multiple offices, including our group out of Salt Lake City that is really experienced with this. So they reviewed it as well, and then you've got typical plan reviews by RDOT.
Okay. The next question was, what specifications control differential movement of the bridge ends during the slide?
Okay, that's a good question. So again, with this being design bid build, that was all contained in that special provision. So as well as the contractor slide plan. So what we ended up using was a tolerance. This is for the differential, I guess, between the position of the two bridge ends as you're moving laterally. That plan was set up to move both of those in, simultaneously, and then they were supposed to monitor those positions, and if they got within 2 inches out of sync in position, they were to deliver a warning, and then there was an all stop at a 4-inch out of sync. But again, I we were fortunate with this one being a single span bridge and not having the near as much constrained at those bridge ends that wasn't as big of a deal. But I don't those constraints weren't hard for them to achieve, if memory serves. It came across really smoothly and evenly.
Okay. The next question, could you speak about earthquakes and bridges and really what measures were taken for this project? I was wondering if there was anything special for ABC.
Mm-hmm. Okay, so that's a good question. This project may not be the best one to address that because it is located in seismic zone 1. It's a simple span bridge, so it didn't have any explicit seismic design. So yeah.
Okay. The next one was, how much did the ABC option cost compared to maybe conventional construction, and how did the final cost compare to your estimated cost?
Right, good. Yeah, so got some information on that. So the total project cost, not just bridge, but all the roadway, the entire project was about $12.6 million for these two bridges, compared to our estimate, which was about $10.2 million. So there was a good percentage, increase over the estimate there. The bridge cost came in at a very high $402 per square foot, which is significantly higher than a non-ABC bridge. I think a lot of that is due to the fact that this was a first time use in Arkansas, going through the line items, it was clear that the temporary false work and the slide system and the jacking system were the main reason for that discrepancy. You know, for instance, we had, you know, the temporary false work, you know, was nearly, you know, $1 million by itself. I mean, so that was, you know, that was the biggest change. But I would suspect with continued use, you know, that the comfort level would come up, and also I think it just has to do with the fact that it's design, bid, build, and you're you know, you're a little bit blind to what they're going to use.
Okay.
I'd like to add also to that. You know, about the time frame that this project was let, our average bridge cost in Arkansas was probably around $150 per square foot. And as Fred said, this one was right at $400 a square foot. For this project, pre-bid, I would have expected costs between $200 and $250 a square foot, just because you have interstate traffic and working in the median on off both shoulders and stuff like that. So it was a little bit of a sticker shock to see the $400 a square foot.
Okay. We're going to go ahead and turn it over to Jugash for the questions that have come in during the presentation. And Jugash, are you there?
Yes, I'm here, Paul. I'll go ahead and ask the question. Can we switch to slide number 8, please? The question is, the slide number 8 shows a bolt-on rail. Is that a tested rail?
No, it is not tested for MASH.
Okay, but it was accepted for use.
Yes, this project was let before the MASH requirements went into effect.
Okay. The next question is on slide number 18. It says 120 days for bridge replacement and 20 days for box culvert replacement. Doesn't the 20-day box culvert replacement requirement pretty much dictate precast units?
That's slide 19, and yes. Yeah, it's the next slide, Fred. Yeah, the 20 calendar days is pretty much going to require precast box sections. And those are used quite often in Arkansas.
All right, thank you. Next question, is there any limitation for the bridge span length and weight for using lateral slide construction method?
That's a good question. I'm sure there is some practical limit. I knew that we were, at least on this project, we're not approaching that. So I'm sure that'd be just a case by case decision there.
Okay.
Yeah, with this being our first lateral slide in Arkansas, I'm not sure that we're the appropriate agency to ask that question to. But maybe
Utah.
the doctor, yeah, or Utah.
Right. Next question, gentlemen. It says, any issues with bounce during the pulling slide? That is overcoming static friction versus strand sag.
Yeah, so there was, I think on the first bridge that we slid, which was Bridge A, the westbound bridge, that one, it was I guess a little more, you know, somewhat less smooth than the eastbound bridge. You know, it would load up the strands, as you said, and move a few inches. So it was, yeah, so it wasn't completely smooth and continuous throughout that whole process, but it didn't seem to provide a whole lot of impact. And then the eastbound was, for whatever reason, it was noticeably smoother. I mean, it would break that friction free almost immediately, you know, so it was very smooth, continuous operation on the eastbound.
Okay, thank you. Next question, what kept the superstructure moving in a straight line during the slide?
So yeah, that's a good question. On as part of their slide plan, of course, we've got semi-integral end vents on both ends. Yeah, so we ended up using a guide system on one of the bridge ends to keep it from walking longitudinally.
Okay, thank you. Next question, can you please restate how much traffic downtime was associated with this slide?
Absolutely. So the short-term closures were both on the order of 8 days.
Okay, thank you. Next question, to expedite the construction process, was precast approach slab considered as an option in lieu of higher strength concrete for the approach slab?
So yes, it was considered. So it was is basically my designer's preference to use the cast in place there. It's just a personal preference. I know it's been done both ways, but so there's some time gained, of course, with the precast, and we initially did have to do the approach gutters that way, but just in order to get the best fit to the ground and the best long term. That was my opinion.
Okay, thank you. Next question, what was used for sliding in terms of materials? And what was the friction factor? Lubricated, parentheses. Yeah. Any guiding system in use during the sliding?
Okay, repeat the last part of the question, please.
Any guiding system.
Right. So yes.
During the slide.
Gotcha. Yeah, so that actual slide system consisted of a PTFE, a Teflon track that was placed on the top of the caps, and then we had the stainless steel plate that was embedded on the bottom side of the semi-integral indents. So that PTFE and stainless steel was our low friction surface. We did have a guide system, like I mentioned a minute ago, to keep it from walking longitudinally, and then I don't recall the exact friction factor, but we can get that for you.
Okay. Did the contractor have previous bridge slide experience prior to this project?
They did. Yes, my knowledge, they had done a similar project for Oklahoma DOT, among others that I may not know about.
Okay. How was the lateral slide synchronized at each bend to ensure the bridge moves at the same rate at each?
So yeah, again, that with it being fairly unrestrained at both bridge ends, with it being a simple span there, it was not as much of a concern. But we did monitor it manually with essentially just with steel tape measures, to know where our starting and stopping points need to be. And again, we had the tolerance that was in their slide plan, and to my knowledge, they didn't have any issues staying within that tolerance.
Okay.
I would like to add one thing to the previous question, Jigesh, about contractor experience. This same contractor was actually our representative on our RDOT FHWA committee that we put together in 2013 and 14. This contractor was our contractor representative, so he kind of had a little bit of an inside head start.
Okay, thank you, Rick. Please explain the need for vertical jacking within the pockets.
Okay, so the jacking had to happen at a couple different times. So of course we start off building the bridge building the superstructure on the temporary false work. So we have to raise it initially to get it to install the slide track to get that on the sliding surface. Once that it's installed, slide it laterally, and then we have to jack it up again in order to remove that slide track and to install the permanent bearings.
Okay, thank you. How many bidders did you have, and what was the spread in contractors' bids?
So I've got some information. Did you want to answer that, Rick?
I don't have the information in front of me right now. If you do,
okay.
please share it.
Yeah. So the winning bid, like I said, was around, the total project was, the A part of the bid was 12.6 million. There were only two bidders, and I think the next bid, it was a good percentage higher. I think their base was around 18 million.
Yeah, I have time for maybe one more question. How much camber was built into the permanent lower cap, and was there a fit up issue with the bridge cap?
So there, don't recall right offhand what that camber was. So there was a it was a fairly low deflection that was predicted on that, and it seemed to fit up really well.
Thank you. I think I'm almost out of time. We do have other questions which will be answered on the website. So with that, I'll turn it back to Atarod and Mary Lou. Thank you very much, Rick and Fred.
Thank you.
So thanks to our speakers, and thanks to Jugish and Paul that moderated this webinar. Again, please note that the 2021 Virtual Accelerated Bridge Construction Conference is just a couple of weeks away. So we hope that you register and attend the conference. We will not be able to archive the presentation. It's a great opportunity to learn what the rest of the world is doing in the ABC area. So on that note, we will conclude our webinar today and hope to see everybody with us for our next monthly webinar. So long.